Hello everyone, I'm glad to share my recent research with you here. In this brief presentation, I will talk about the novel regularization technique presented in this paper, named Adversarial model perturbation. This is the outline of this talk. Effective regularization schemes alleviate overfitting and improve generalization. Look at the two figures. The left figure sketches the model's behavior without regularization, which can only achieve the large generalization error on relatively small capacity. However, in the right figure, the model can achieve a small generalization error on a relatively large capacity. Some researchers have found the model neural networks may have a different behavior, that is, the double descent. Nevertheless, well-regularized neural networks consistently achieve better performance in practice. Previous work suggested that the flat minima can improve generalization both in theoretical and empirical perspectives. So in this work, we propose a powerful regularization scheme principled by the objective of finding flat minima. In adversarial model perturbation, we minimize an alternative AMP loss. The AMP loss is derived from the empirical risk by applying the worst perturbation on the model parameters. As sketched in the figures, it applies a max pooling operation on the empirical risk to seek a flat minimum. In the AMP training procedure, we adopt a mini-batch HGD for solving the min-max problem. We firstly update delta to maximize EM loss via gradient ascent, and then update theta to minimize EM loss via gradient descent. We implemented the AMP with PyTorch. The AMP is very easy to use. You can just replace the optimization steps with the following list to regularize your neural network models. Now we will give some theoretical justifications about the AMP. We assume that the loss surface of each local minimum in EM loss can be locally approximated as an inverted Gaussian surface gamma with a mean vector mu and a covariance matrix kappa. Under the locally Gaussian assumption, the empirical risk is minimized when theta equals mu, and the minimum value is c minus a. The minimum value of the AMP loss is the empirical risk at the location in the narrowest principal direction of the cross-section of the loss surface, where sigma square is the smallest eigenvalue of kappa. It is clear that gamma AMP star, although related to the minimum value of empirical risk, it also takes into account the coverage of the surface around the local minimum. Thus, you can find a flat minimum by minimizing the AMP loss. On the other hand, AMP can regularize gradient norm. Consider that n equals 1, which is in fact used in our experiments. The AMP training is equivalent to EM training with an additional term. Thus, the AMP training algorithm effectively tries to find the local minima of empirical risk that not only have low values, but also have small gradient norm near the minima. Note that a minimum with smaller gradient norms around it is a flat minimum. Now we have given the formulation and justifications of AMP. We also conducted extensive experiments to validate the effectiveness of AMP. Here is a setup of our experiments. Firstly, we find that AMP has a larger training loss but smaller test loss than EM training. On 3 image classification benchmarks, AMP achieves the best performance among the compared regularization schemes. Furthermore, AMP can improve the model's performance over powerful data augmentation techniques. Besides, AMP is capable of reducing the calibration error of neural networks. We also investigated the relationship between loss values and the perturbation sizes. The proper perturbation size helps the model achieve the best test loss. We visualized the landscape of selected minima of EM and AMP. We found that the minima found by AMP are flatter than EM. That is all. Thanks for listening.